All right, guys, welcome back. So today we're going to be going a little bit deeper into Caustics. We're going to be focusing on rendering quality, performance optimization, and then tweaking a few inputs to make things more modular and lead to more interesting effects. So I want to thank Samil in the comments for mentioning that we should be improving rendering performance. I'm going to go into the technique he mentioned in just a little bit. Um, and let's get started. So what we're looking at here is exactly where we left off last time. If you haven't done that tutorial and followed along to get to this point, I highly recommend you do that now. I'm not going to go over any of that again. So basically just assuming that we're all starting from the same place here. All right, so where are we going? We are going to something like this. So we can see the original on the left, the new on the right. And what we'll be doing is adding some features to one, as I mentioned before, improve performance, as well as quality, giving us some more modularity in the way that we are rendering things, as well as rendering color. And one that I really like is using a map to actually distort the light direction that we're feeding in to our caustics that lead to some pretty interesting effects, especially when overlaid with the noise that we're using to represent the surface. Cool. So let's jump into things and get there. So before we do that, I'm going to build a quick utility for us to track performance. So if we mouse over a component, you can see 5 milliseconds is the cook time for all of the GPU cooking for the children of this node. In our new caustics, it's about 1 millisecond. So we're looking at 5 milliseconds. Well, I guess this isn't rendering, like 2.5 milliseconds to 5 milliseconds. So about a double the performance from our new setup. And we're going to want to be able to track that as we are working. So I'm going to get an execute that. I'm going to turn on frame start. I'm going to get a constant chop. And what we're going to do is just say op constant one dot par dot value 0 dot val. Remember to use dot val equals op caustics original dot and now we need to figure out what member we can use to access that information, which I will do by just clicking on the help page and searching for GPU. We'll see that there's this member called children GPU cook time, which we can then drop right here. Cool. So what's our error? Seems like it shouldn't be there anymore. Cool, it's gone. All right, so now we have our chop tracking our cook time. I'm going to throw a trail down and we'll put in a filter for good measure. And then we'll call this performance. And this can be GPU. Cool. All right, so now we've got this working. Let's split. Get this over here, make this a chop viewer, and view our chop rather. All right, cool. So now let's jump in and start to make some changes. All right, so what is happening when we're instancing and how can we make it a little bit lighter? Instancing, as I'm sure most of you guys know, is just taking a source geometry and copying that geometry to every point that we tell it to copy onto. Those points are defined either via a top, where pixels are points, as is the case here, chop, sop, etc. Our input geometry is then copied to every one of those. So we have about a little over 1 million points. We have a box. We're copying that box onto all of our 1 million points. Now, a box is composed of 24 points, 6 primitives, 24 vertices, and 6 polygons, which means that we're copying all of that weight a million plus times to get to our rendering here. That gets pretty heavy pretty quick. So what we can do is use a geometry that has a lot less going on, which will enable us then to lighten our instancing workload a lot. We'll do that by doing an add sop, add points. We'll notice that there is just now 1 point. We will convert that sop to particles per point. We'll see that we now have just 1 point, 1 primitive, 1 vertex, and 1 particle system, which has 1 particle in it. Before I wire this in, I'll drop down a constant mat, and then finally, let's see what happens. So if we're taking a look, we're at 5.5 milliseconds or so. Once I connect this over, that immediately drops down to just about 2. So really got double, maybe a little bit more than double performance gain just from that alone. Cool. So what are a couple other things that I want to mention? One thing is, actually, I believe that if you were starting from where we started last time, you probably need to flip draw over draw on, and that will reduce some of the clutter in here. So if we have it off, we turn it on, you can see that that reduces the clutter quite a lot. I'm going to get rid of this now, and we can then toggle this draw over draw limit to define how much we want to, let's say, weight the high concentration areas or our caustics more and make them brighter. So as we go up with the overdraw limit, we can see that the bright spots are left only in the areas where there's maximum concentration and where our caustics have the greatest intensity. I think something around 3 is nice, but depending on your other parameters, you'll probably want to tweak that a little bit. I will also note that if you want to use a line mat instead of a constant mat, it does have a little bit of performance impact. We can see here we're hovering maybe 20 milliseconds, or sorry, 0.2 milliseconds below where we were at with the constant mat. You will need to have a draw over, or sorry, display overdraw on for that to work. If you have it off or was off and you don't turn it on, then your line mat's not going to do anything. So why would you use a constant mat instead of a line mat if a line mat has a little bit better performance? Well, the main reason is color. Because this line mat is only really able to color things via the colors on the material. We can't color things per instance. We need to be able to use the constant mat if we want to get instance-based coloring, which in this case, I do personally. So I'm going to put the constant mat back on, but just so you guys know, you can change that out for a line mat. Get yourself some tenths of a millisecond back as long as you remember to keep display overdraw on. And then just one other thing to note, you probably want your render quality pixel format to be 16-bit float. That's going to make sure we represent a nice range of values in our render, but going to 32-bit float is definitely, actually here, let's do this again, is definitely going to change things. So here, if we go back, so now we're looking at our performance, and if I change from 32-bit to 16-bit, we can see that our performance basically doubles again. If you go down to 8-bit, you get a little bit more, but that generally, I think, results in a lower render quality. So 16-bit is nice as a sweet spot. Cool. Now we'll keep that up. Keep that up. And okay. And then it's not working. Oh, there we go. Okay, we'll let that there for now. Okay, so now we have our render working a little bit better. I'm going to open my parent parameters, drop that resolution, change my resolution to go back to 2048 by 2048. Very good. All right. So how do we get some color in there? We can get color by simply using the instancing to put color onto our different points. So we'll grab an in, route this noise into it as the default. We will fit this based off of the parent parameter's caustic resolution. And boom, boom. All right, we'll make a null, call that color. And then we will drop this, on the color op. All right, so we're not seeing any color. What's up with that? Boom, color. So now we have a bit of a problem because, as I mentioned before, turning the display overdraw on is one, necessary for lines, but you can't color with lines, and two, really helpful for making this render look a lot nicer. But we still want to have color. So what do? What we do is use a render pass, drag and drop this on it, and because the display overdraw is only a render specific parameter, we can actually render this geometry twice with minimal overhead additional because of the way that TouchDesigner handles the render pass, and use that to overlay color so we still get the benefits of our display overdraw, but with color as well. And so we'll do that simply by multiplying these two together, making sure display overdraw is turned on here. And there we go. So now our result is the product of our overdrawn caustics and the caustics rendered with color. And things are already looking nice. So what can we do? Let's first customize our component a little bit. I probably want to give the overdraw limit as a parameter here. Let's take a look. So yeah, we do have a little bit of performance impact from our coloring. So we can see it goes from, let's say, somewhere around 2 milliseconds to somewhere around 2.4, 2.5, which is meaningful. So it's really up to you whether that trade-off is worth it. What I'm going to do is probably throw in a switch. That switch is going to have a parameter-based index. We'll call this render color. You notice when I drag and drop, I can just make this immediately referenced here. Pretty handy. We'll pipe this comp in there, and we'll work that in. So if you keep the blend inputs off, then the op that is not selected is not going to be cooking, at least if the viewers are turned off. So we can see here that this op now is actually not cooking at all because we are selecting just the render with no color. And because the switch has blend inputs off, it means that our other comp's not cooking at all, which means you get to realize the full performance benefit of having just the color, or rather just the black and white render, mono render. Which is then pretty easy to just tweak. Pretty easy to just tweak using our, let's make this a toggle, using our parameter. Boom, boom, which is nice. And then just to close out the example, if I turn this on and have the index be something that's between, we can see now that we're cooking. So we'll keep this set to off. We'll keep this indexed to our parameter, and that'll give us a way to turn color on and off, which means you get the performance benefits when we have it off. Also, as you'll see, display overdraw limit here is helpful for refining exactly that highlight in the caustics. And if you have colors on, I'm going to tweak it a little bit further. Cool. So now we have a little bit better post. What else can we do? One thing is add a little bit of feedback between the blur and the luma blur. So we'll throw some feedback in there, make it a comp. Put this back in, we'll add those together, we'll drop this on there, that's filling up. Level. And cool. So all we're going to do here is just use a very basic feedback loop that is going to just blur what we're passing into the Luma blur a little bit to make it less reactive to the negative space kind of in between the concentrated caustic areas. So, whoops, let's get back here. So, looks like that's a little bit high. Maybe let's go something like this looks pretty good. Maybe like that looks pretty good. Um, and we'll turn this filter weight back up. Actually, I'm probably just going to parameterize this filter weight. Black filter. Oh, I'm getting lost. Okay, yeah, I'm gonna take this black filter weight. I'm gonna add it here, which is not playing very nicely at the moment. Okay, maybe this will work now. No, it won't. Okay, that's fine. Do it manually. Black filter weight, and we'll make that go up to, let's say, 15. Black filter weight, boom, and now we can adjust our filter using this. And you can see that our quality is definitely a lot higher with the higher filters, especially if we, or sorry, versus when we are doing a unfeedback looped input. So let's say, for example, just the raw input, you can see all of this aliasing. It's pretty horrible. And with just the blurred input, it's a little bit better, but it kind of looks, I don't know, not very good to me. But I really do like how it looks when we combine the blur with the feedback. It really lets you hone in on the level of detail that you want, and things stay pretty smooth and don't really alias that much. So I like something around 9, or sorry, 5. And maybe, no, I'm probably just going to leave that somewhere around 0.75. Cool. So that's great. Things are already looking pretty good. Because our performance is a little bit better, let's up the resolution, get some more points in here. Back up to 4 milliseconds. It's not crazy, and I do have the screen recording going, so things are costing a bit more than they would on your machine. All right, so now our post is nice and set up. Things are looking pretty good. One other thing that I want to add is a threshold. And that threshold is going to be placed right after this render. And what that's going to do is basically just let us cut out some points, or rather cut out some areas of space, mask some areas of space that are less dense. So if we, oh, that's a transform. Oops. We take a threshold. So we can see that by changing the threshold value, we are either excluding or including more regions of space based on how dense they are. So if we go back to our full render, you can see that here, getting the threshold involved, you can really dramatically take out the density if you really want to. Now, there's a couple different places you could put this. So we can see maybe instead of having it there, we like to, well, actually, that'll cause some problems. So I'm just going to keep it here. I'm going to keep it here, and I'm going to keep my threshold pretty low. And then I want to soften it a lot. Yeah, there we go. That's looking nice. All right, cool. So yeah, you want to make sure you turn the softness the whole way up. And that will make the mask work a lot better. Cool. All right, so I'm gonna leave that at around here. Cool. All right, sounds good. Let's get our noise a little bit different. Hmm. Well, we'll come back to this anyway. Um, whatever. I'm gonna get that back anyway. Um, okay, cool. So our post rendering is, or rendering and post rather, is looking a lot better. We now have the ability to throw some color in there. We have a parametrized Luma blur that's looking a lot better. And that's great. We'll get rid of this box because we don't need her anymore. And there we go. Things are looking pretty good. So what are a couple other things that we can do here? So one that I definitely want to do is change the light. So if you remember from last time, I'm going to get rid of this now. If you remember from last time, one of the assumptions we made when we were working with our light was that the direction here was just straight down. That's fine. Not really limiting. I like the effects here. Things are looking good, but I want to be able to have a little bit more flexibility. So what I want to do is add a map that we'll use for light direction instead of taking it from the, or rather just taking it as a straight down in all cases. So that should be pretty straightforward. All we'll need to do is have a map. So I'll use a noise and then a null. Call this lighter, and we will wire that into our caustic simulation. Cool. So now what? Now we have to grab it, which we can do here. All right, nice. So we can see something's happening, although it looks chaotic at the moment. What can we do about that? So let's first get our noise right. 32-bit float, mono. Let's make it 512. And okay, that is a good place to start, although shit's still looking crazy. And the reason for that is because right now our light is coming from many, many places. And because it is ranging as noise ranges from -1 to 1, the values can get pretty crazy because we don't have all of the light coming from the same general direction. Right? If you think about a light source, the sun, sure, not all of the light rays are coming directly perpendicular to the plane of intersection in the real world, but they're generally coming in the same direction, i.e., more from the sun than from other places. Normally, not always. So, what do we have to do? All we have to do is use this noise to perturb some light vectors that are coming from the same direction. So we'll grab a constant, wire that in, set that to 0, that to -1, and that to 0. And we'll make it 32-bit float. Finally, setting the noise to input minus noise. Offset of 0, amplitude of 0, and boom. This is now exactly back where we started, which is good. But what we'll see is if we make the amplitude greater, maybe the exponent a little bit greater too. So what we're doing now is essentially using this noise map to, oops, there we go. We're using this noise map to perturb the light that is coming directly down. So this constant is using our same vector as we were using here, light coming straight down, and then we're just applying this noise to it to perturb things a little bit before it hits our simulation. I like this a lot. This allows you to really play around and get some pretty complex effects, especially if you start changing the input noise at the same time. Uh, you know, let's think maybe like our gain can go up, or sorry, our spread can go up. Our gain can go like way down. Let's maybe make the period bigger. Not quite so big. Maybe a little bit more gain. All right, so like now we've got some interesting stuff going on. And I think that's pretty cool. Removing this, let's maybe transform our light a little bit. 0.5. What's this going at? 0.5. Let's maybe plus 20, just so that they're actually, no, that's not what I wanted. I want 3, just so that they're changing at a little bit different speeds. All right, and so with that, we now have a refined caustic algorithm that is, 1, looking a lot better, 2, running a lot faster, and 3, has the ability to take in an input map for the light direction that will allow you to really generate some interesting and complex results with some exploration. So, and then I guess just to round things out, take a look at this. Okay, so even after all of that, we are still running at under 4 milliseconds, and that's using 1500 caustic resolution, which is a lot more than we had before. And, you know, 3 or 4 milliseconds is firmly within real time. So even after all those changes, adding the resolution and improving the render quality, even if we render it as color, now it's a little bit over 4, but things are still looking pretty good. Maybe to finish it off, we can throw this threshold parameter in here. And then maybe I'll also add the light perturb amplitude and the exponents. Light perturb exponents. Cool. So now we have what I think is a much more refined algorithm. Lets us really hone in our rendering output as well as the kind of form and function of the actual effect itself. So that's it for today. I hope you guys enjoyed, and I will see you next time.